In the previous lecture, you have seen the simple and natural axiom system due to Peano and Dedekind. This is the first foundation stone we have laid. In this lecture, you will see addition being defined rigorously using a very important theorem known as the recursion theorem. This is the first major application of the induction principle, and the recursion method is also called the method of definition using mathematical induction. I had given this as a problem in the form of question 2 in the exercise to the first lecture. If you have tried to solve this problem, you would have realized that it is a very non-trivial exercise. The proof of the recursion theorem seems to be rather difficult and too abstract in most books. I will try to make the proof simpler by giving you some diagrams to make the idea clear. Once you understand the idea, the proof really becomes simple. You are advised to spend some time studying this theorem very carefully, and I can assure you this will be a very rewarding experience. Why do we need the recursion theorem? You may have encountered the following three words in mathematics used very often: and so on, ... For example, when one defines n factorial, you say 1 factorial is equal to 1, 2 factorial is 2 times 1, 3 factorial is 3 times 2 times 1, and so on. Another example: Sn is equal to summation k equals 1 to n ak. This is usually defined by S1 is equal to A1, S2 is equal to A1 plus A2, and so on . The recursion theorem makes this very precise, and we will see many examples of the recursion theorem used in mathematics. Three immediate ones are the addition, multiplication, and exponentiation. And we will see that all the properties of arithmetic which we learn in elementary school, like associative law, commutative law, distributive law, can all be proved by means of the recursion theorem. The proof of the recursion theorem will be broken up into two parts: the uniqueness part, which is fairly easy, and the existence part, which is very tricky. The recursion theorem says that there exists a unique function f from n cross n to n, so that for all m and n natural numbers a, f of m comma 1 is equal to s of m. Recall that little s is the successor function, and b, f of m comma s of n is equal to the successor of f of m comma n. The general definition of a function will be discussed in the lectures on axiomatic set theory a few weeks from now. For the time being, it is enough to know that a function f with domain n cross n and taking values in n is a set of ordered pairs m comma n comma p, where m, n and p are natural numbers, with the pair m comma n itself being an ordered pair, with the property that if m comma n comma p and m comma n comma q are in F, then P must be equal to Q. Now, to satisfy part A of the theorem, we can simply define F of m comma 1 as the successor of m. This is a legitimate definition because, recall, the successor of m is a well-defined object in the set of natural numbers by PA1. Let me repeat some of the things again. You must think of a function conceptually as a set of ordered pairs. The first element in the ordered pair belongs to what is called the domain of F. And the second element in the ordered pair is in the range of F. Conventionally, the second element is denoted by F brackets first element of the pair. In the situation at hand, the first element of the ordered pair is itself an ordered pair of natural numbers. And the second element is simply a natural number. Let us now look at property B. Property B tells us that when the pair m comma n is in the domain of F, then the pair m comma the successor of n is also in the domain of F. Moreover, what we want in property B is that the value of the function at m comma s of n should be equal to the successor of the value f at m comma n. So one may say, what's the big problem? You simply define f of m comma s of n is equal to the successor of f of m comma n. Well, there is a logical difficulty with this. On the right hand side, we are already assuming that F, which is a set, has already been defined on n cross n. And we are trying to now say define f at m comma s of n as the successor of f of m comma n. So there is a logical problem, and the construction of f is fairly tricky. As I said earlier, the proof of uniqueness is fairly easy. So let's begin with the uniqueness part. To this end, suppose that f and g are two functions, both having domain n cross n and taking values in natural numbers, satisfying both the properties A and B. Fix an m belonging to n and let capital M be those natural numbers such that the value of f at m comma n is equal to the value of g at m comma n. We will prove that the set capital M is the whole of capital N. And we will do this using the principle of mathematical induction, the weak principle of mathematical induction. Base case: 1 belongs to M. Why? Because by property A, f of m comma 1 is the successor of m, and since g also satisfies this property, g of m comma 1 is also equal to s of m. Inductive case: suppose that a natural number little n is in the set capital M. Then, by inductive hypothesis, the value of f at m comma n is equal to the value of g at m comma n. Hence, the successor of the left hand side is equal to the successor of the right hand side. But by property B, the successor of f of m comma n is simply the value of f at m comma successor of n. Similarly, the right hand side is equal to the value of g at m comma s of n. Thus, the successor of n also belongs to M. By WPMI, the set M is equal to capital N. And since M is arbitrary, it follows that f of m comma n is equal to g of m comma n for all m and n in natural numbers. Hence, f is equal to g. Well, recall f and g are both sets. Two sets are equal if one is a subset of the other and the other is a subset of the first. So, here, since both f and g have the same domain So as sets of ordered pairs, the first element in both the sets F and G are present. And for any first element m comma n, we have shown that the value of F is equal to value of G. So the ordered pair m comma n comma p is equal for both F and G. This proves the uniqueness. Let me pause the proof here and tell you that this technique which we have used in uniqueness will be repeated again and again and again in the proofs which are to follow. So I suggest you pause the video here, study it very carefully, go through each and every definition, and I shall continue with the proof of existence in the next video. Let me summarize today's video. I proved the uniqueness of a binary operation f assuming its existence. We shall see that the binary operation has all the familiar properties of addition. Only basic concepts from set theory were used. More specifically, the notion of an ordered pair, function, binary operation, and Cartesian product of sets, in this case n cross n. The notion of a set will remain a primitive, undefined concept in the development of the subject, and ordered pair will be axiomatized. So just a note on the coloring scheme. Until a concept has been defined precisely, I shall be coloring it red. Concepts which have been defined. For example, I defined function in today's video. The binary operation was defined as a special case of function. The Cartesian product is in turn a special type of object called relation, which is defined in terms of ordered pairs. So I can safely assume that they have been defined. A word of useful advice. You should go over the previous video and today's video and analyze exactly which assumptions have been used. For example, study the two theorems I proved in the last class and see for yourself that what went into the proof of those theorems. So, with the comments I have made about undefined things, so far you can check that the theory is on a firm logical footing. In the next video, I shall be taking up the existence theorem for the basic recursion theorem. See you till then.